And this was another one of Colin de Verdiere's ideas was, well, his observations was that, okay, what we need in order to make this construction work is we need that our distribution that we're dealing with on the right-hand side to belong in a certain Sobolev space. So we need like a certain amount of convergence. We need it specifically to be in H -1. And unfortunately, the operator that we are dealing with just misses this Sobolev space. It just falls out of it. So there's a nice containment, but going the wrong direction. And so here's where Colin de Verdiere's second great idea came in. His idea was essentially to project the spectrum of this distribution, or to project this distribution to the non-cuspidal piece of the spectral expansion. And so I should have done something smarter, but I'm going to instead just scroll back for a while. And basically, since delta is in some negatively indexed Sobolev space, we can write a convergent spectral expansion. And basically, all this means is just kill off this term in the spectral expansion. That's all that non-cuspidal projection is. Okay, and so when I do this, I'm in the proper Sobolev space that I can actually perform this restriction and Friedrichs extension of this operator. And so I should say he wrote this series of papers in the 80s, but this problem kind of was not for the best of my knowledge, not explored for quite some time. And I think as he tells it, Paul Garrett, after becoming full professor and having his children move out of the house, had time to read papers in French and wanted to finally understand what was happening in this paper. And he, with Enrico Bombieri, wanted to sort out, okay, what actually remains when we perform this construction? What of the spectrum is left? And I haven't put a date on this theorem because it was proven at least 10 years ago by now, but it's in a 2020 manuscript on the archive. And so what this says is if I take my new operator as the restriction of delta to the kernel of this projected distribution, intersected with test functions, and I take the Friedrichs extension of that thing, then the spectrum of this operator, or the S values in the spectrum, is completely contained in the online zeros of these L functions. So a very great result. Well, the problem is, well, we really love the containment to be going the other way. That's really the Hilbert-Poya conjecture, I suppose, which is all fine and good if we have equality, right? No one cares then, and then everyone's happy. But of course, we don't have equality, and we know that for sure. So the reason we don't have equality is that we can understand how the eigenvalues of this operator are distributed, and that distribution is in conflict with how we believe the eigenvalues of zeta are distributed on the critical line. Namely, if we assume the pair correlation conjecture, then at most 94% of the zeros could be appearing in this spectrum. But maybe more problematically is that that's an upper bound, right? And there's no guarantee that we have any, and there's no guarantee that this spectrum of this operator is not empty. Okay, which is very sad. And yes, it's unlikely. Yeah, it's almost certainly empty. Right, that's exactly the thought. Yeah. So this is exactly the thought. Why would some zeros of zeta be special? It's got to be empty. Okay. Great. So sad, but you have to investigate something when it's that interesting and thrown in your lap, right? Okay. So I guess we can ask, how would we prove such a thing? I actually got a very grumpy question once about how could we prove such a thing if we don't even know the spectrum exists? Which I thought was silly because we're mathematicians and maybe in physicists, I guess, but we prove things about things that don't exist all the time. So anyway, so the proof looks something like this, and this is where I feel like there's some nice connection with some of these physical solutions. So understanding these eigenvalues really comes from looking at the spectral solution to this differential equation. And so I can write, I can find a solution to this differential equation, mapping out kind of the method that I spelled out at the beginning, where I write theta as spectral expansion. Remember, we killed off that cuspidal little piece, so that's not there. And then we just divide by the eigenvalues, and that is my solution FW, right? And furthermore, I can meromorphically continue this solution by a nice regularization argument. So basically, I add and subtract these combination of UW terms in here, and I get that the meromorphic continuation of my solution is given in this way. Okay, and so an interesting thing to note about this meromorphic continuation of the solution is that we have this extra term that pops out. So there's not this really nice S to 1 minus S symmetry that we like to see in L functions. There's an extra term here. And this extra term is important because if it weren't here, we would actually be able to prove the Riemann hypothesis using this method. There's a nice argument. But furthermore, if it weren't here, the same argument would work to show that all of the zeros of, say, Epstein zeta functions are also on the critical line. So it's probably good that it's there because we'd hate to prove false things. Okay. But a nice little thing that happens here. So and this J function here that we use for this regularization and meromorphic continuation of the solution can actually still analyzing the eigenvalues that appear here, and I should have put on here. There's for the Friedrichs extension, we also need this boundary condition that's solved, and kind of analyzing these solutions allows us to say something positive about the zeros of zeta, or at least something non-sad about the zeros of zeta. All right, so what they were able to show in this paper was independent of whether or not the spectrum of this operator is empty, that this J function that occurs from this meromorphic continuation can kind of identify where certain zeros are more than average spacing or half average spacing apart, is basically what these, very small written results are, but they gave us a way of identifying zeros that are maybe less than half average spacing and average spacing. Okay. Okay, so as far as this project, this kind of sparked my interest into looking into differential equations involving automorphic forms and automorphic distributions. The hope is that maybe some other spacing results could be gotten from further analyzing what's in this work, and especially if we were to extend to other L functions, maybe where less is known about the spacing of their zeros. And in fact, there are ways of extending these constructions. So given the way these given the way these the theory is constructed, there's nice extensions of this to higher rank groups and other types of L functions. In fact, most that should be self-dual might be able to be constructed in a similar way. And then, of course, there's also interest in examining the spectrum of this operator. Okay, so this is kind of the problem that got me interested in, and I've been working a little bit on extending some of these things to other L functions. But this is a kind of a long process here. And in the meantime, I've gotten distracted possibly by some other things that have come up. And so this leads me to the other application that I wanted to talk about. Okay, so I'm likely one of the only mathematicians left here. No, Don probably finds that as a compliment. No, so I won't bother explaining to a group of physicists what a scattering amplitude is, because I'm sure I will do it poorly and end up in the river again, like Sunil suggested. But basically, the idea is for a scattering amplitude, we want to assign some sort of probability for a given initial and resulting state to occur in a given scattering process. Yes. I'm risking the tomatoes for not describing a scattering amplitude. Oh, for describing them? Or for calling you a physicist? Okay. Yeah. Well, I just want to make sure you were awake back there is all. I'm glad to know you're still here. Perfect. So you were supposed to be gone by now. No, I'm just kidding. Okay, so specifically in closed type 2b string theory, we can make this the 4 graviton scattering amplitude is a function of like 2 major variables. So we have the energy, which is given in terms of these Mandelstam invariants and what is sometimes called the string length alpha. And we also have the genus G here. And if we expand out in the alpha variable, there's an analytic piece to this expansion, which we have written here. So this is analytic in these sigmas, which are functions of energy here. And its coefficients are functions of G. And so we know the first coefficient in this expansion due to the Einstein-Hilbert constant. And the other ones obey certain symmetry properties and have been found that we'll talk about in a moment here. So these higher coefficients we know are left G invariant or GZ invariant. They have moderate growth, and and some of them at least satisfy differential equations up to some point. Okay, so we have this first coefficient already. So of these non-constant coefficients here, or I guess the later coefficients here, the next 3 coefficients are given by 0, 0, 1, 0, and 0, 1. And they're given by solutions to these differential equations. And so the first 2, at least on this SL2 case, are exactly eigenfunctions for the Laplacian. And specifically, they're non-holomorphic Eisenstein series at 3 halves and at 5 halves here. And so in the last case here, the coefficient is given by a solution set equal to this Eisenstein series squared. And so this is what we've seen, a specific form of what we've seen in Ksenia's talk yesterday specifically. So, and in fact, more generally, what we saw was a differential equation of this form set equal to a product of 2 arbitrary Eisenstein series. And so more generally, we'd like to look for solutions of this for other alpha and beta values as it arises in certain correlation functions, and for alpha and beta being integers in the study of modular graph functions at step 2. So we talked, Ksenia spoke yesterday about finding a Fourier solution. But I want to talk about finding a spectral solution for this problem. And in this case, so if I want to use the method that we outlined at the beginning, if I want to write a spectral expansion for, say, the right-hand side and try to divide by eigenvalues, I run into a problem immediately, and that is that these Eisenstein series not only aren't in L2, they're actually not in any negatively indexed sublove space. And that's due to this constant term in their Fourier expansion. And so following ideas of Verdiere, we circumvent this problem by taking this product of Eisenstein series and subtracting off a linear combination to kill off this constant term. So for alpha and beta large, this first term would be like y to the alpha plus beta, and I might want to subtract off e sub alpha plus beta, or something like that. So I subtract off this finite linear combination, and then I have something that is in L2 because I've gotten rid of this constant term, and I can write a spectral expansion, add back in my linear combination of Eisenstein series, and divide by eigenvalues. And so following Zagier's work, what we get in this case is a solution in kind of a spectral form here. So here's my finite linear combination of Eisenstein series that I need to add back in, which these are made explicit, but for different cases of alpha and beta, they somewhat vary. And then here's my sum over Cuss forms. This is just a completed Rankin-Selberg L function as the coefficient for this discrete term. And then when alpha equals beta, there's some extra constant terms that sometimes appear. And for the continuous spectrum, computing these coefficients is more difficult, but the basic idea is to use Arthur truncation and Moss-Selberg relations to compute another completed Rankin-Selberg style L function. And then, of course, we can use a similar regularization argument as we talked about in the Bombieri and Garrett case to get a meromorphic continuation in W for the solution. And so this works for any values C in this region. And in fact, we could use functional equations to kind of extend to other parts of this plane, but there's still going to be these problematic, like little, they're really too faint in the back there, but there's these little lines that we're missing in the C region where the solution isn't exactly computable in this form. And so what happens in those on these lines here is, in fact, we can get the solution to exist in the form of a limit towards the solution written here for particular cases. And those particular cases are where 2 alpha minus 1 or 2 beta minus 1 are non-trivial zeros of the Riemann zeta function. And the reason for this is actually quite simple. In the Fourier expansion for Eisenstein series, this C sub S term is given as a ratio of zeta functions. And so those values of alpha, if 2 alpha minus 1 and 2 beta minus 1 are zeros of zeta, that makes this term 0, basically, is what is happening here. Because those problematic pieces on the line are basically at that region of 1/2 where you're kind of adding and subtracting the same thing back in. Okay, but of course we don't want a special solution. What we'd like is a Fourier expansion. Yeah.
It's the 1 over zeta to S minus 1. I know it's a zeta to S minus 1. It's a numerical, so this term disappears.
Yes.
So it should be better for you if you don't need to compensate to get some function index minus.
Right. It should be, yeah. But the second term only disappears. The first term is still there. Right. Yeah, it's only the coefficient is only on one of them, I think.
Yeah,
but for particular values.
Well, there's no first and second. You always one with this method. That's based on this. You make eigenvalue disappear. The Eisenstein series pathway about capital plus.
Sure, it's not what I'm saying. I'm just saying that it's the second term that if I see more solution to your problem than the problem.
Right.
This problem of having a function that goes to path.
Right. In certain cases, like for certain values of S, right? Like for S small enough. Right.
It's just a question that you say they are bad and maybe they are easier.
Oh, I mean, they're bad when this isn't chosen to be 0, I guess. Yeah. It's not bad when it is 0.
Oh.
It's nice when it is 0.
Okay.
Yeah. Okay. Oh, perfect. We're on the same page. Great. Yes. No, it's simplified when it's 0. And that's why this is, I only have a solution when those are maybe the non-trivial, maybe that threw you off. Sometimes all that negativity and non-trivial, is actually quite nice. Okay. But of course, what we'd like is a Fourier expansion. I believe Daniele's looked into a bit. There is a way to get at least the 0 term from using the linear combination of Eisenstein series here and possibly something from these Eisenstein integrals that appear here. But getting those higher Fourier coefficients is somewhat difficult. And so maybe I'll bring up what I hope is a happier form of this conjecture for Don now and have some appropriate vanishing conditions. So I guess the first version of this result comes from Green, Miller, and Vanhove's 2015 paper for the original motivation where alpha and beta are 3/2 and lambda here is 12. And we think that in the half integer cases, the solution should basically always have this similar form where we can write it in terms of 0 and 1 Bessel functions and polynomials in Y. Okay, and so the cases where this has been constructed, again, this is from the original Green, Miller, Vanhove case paper. And then Chester, Green, Pufo, Wang, and Wen recently did partial expansions in fact, K2 and K3 Bessel functions, maybe higher order ones as well. I can't remember off the top of my head for these cases as well. And then, as Ksenia mentioned yesterday, we found all Fourier modes in most of these cases. In fact, we found all Fourier modes in all of these cases, but writing them down gets quite complicated. Okay, so I didn't want to spend too much time, but I did want to basically touch on the methods here. So in the 2015 paper and what Ksenia was speaking out yesterday, the basic idea was to use this is what Steve Miller calls a guess, but maybe we would call linear algebra to solve this differential equation, and just say, if I have Bessel functions on the right side coming from my Eisenstein series, the only things I could be taking a derivative of are Bessel functions, and so let's match everything up very nicely. And so this can get us very far, but it's computationally maybe annoying and not a very direct method. So Giorgione, Kleinschmidt, and Schlatter have used some of the other methods that I believe Steve Green and Vanhove mapped out in their 2015 paper, and they refer to as the seed method for at least for integer cases. So I should say, so in this 2015 paper, well, the method that was originally used to find the solution was something like what Steve calls a guess or linear algebra. But he mapped out about 3 other ways that one might attempt to solve these different equations, one being the seed method, one being the spectral solution that I talked about earlier. And then the last, actually it was the first one in the appendix, is basically, I think we call it the Poincare series, but that's somewhat misleading since these both involve unwinding a Poincare series, but maybe to fully unwind the product of Poincare series. Okay, so I don't want to go through too much detail because it's the end of the day. This is the 6th talk. So I'll spare you some of try not to wince on the next slides here. But the basic idea is the right-hand side is this product of Poincare series. And basically I can write this as a nice double sum, and I just want to look at kind of what's inside this double sum. And I can write what's inside this double sum as an ODE. So I wanted to talk a little bit more about this like kind of last method. And so on the right-hand side, I have this product of Eisenstein series. So I should mention this method, we don't really know of a way to extend it beyond a squared case at the moment for like mixed products of Eisenstein series. And I can show you where the issue comes in kind of actually, I believe it's right here. So when we kind of look at what's at this being summed up over this kind of double lattice type sum we have here, it's functions of this form. And if we do a nice change of variables where z is equal to x plus iy, this becomes just like a really nice function that we're summing up here. And what remains is to solve a nice ODE set equal to this thing. And these things have solutions in terms of Legendre polynomials, and at least in explicit cases are not difficult to compute. So we compute the solution H, and then we basically sum everything back up, right? And then the idea is we now want to find a Fourier expansion. And so we use the same methods we would use to find a Fourier expansion of an Eisenstein series, or basically the same methods. So what remains is basically to find the solution here, if we haven't already, and then to write the Fourier expansion. And to write this Fourier expansion, we like I said, we use what we use in Eisenstein series. We do some sort of change in variables and Poisson summation. And in the 2015 paper from Green, Miller, and Vanhove, I think they got almost all the way to the full solution, but there was one integral that was left over that was particularly nasty to compute. And it involved the solution evaluated at this weird rational function. Sorry, this is small in the back here. And this exponential here is kind of like a, Fourier type integral you might see, but it's just not particularly nice. And the reason it's not particularly nice is that H solution to the homogeneous differential equation, due to vanishing constraints, involves an arctan. And so this method that they wrote up in the appendix kind of wrote the full Fourier expansion just depending on whatever the solution of this integral was, and left that to be discovered. And so recently, Steve, Danylo, and I were able to work out what the computation of this integral is. It only, well, I won't tell you how many pages it takes because it would be a lie. It would take a lot more than that, but it took a while. But it involved 7 iterations of integration by parts in order to make this arctangent vanish, and we were able to compute this integral explicitly. And so this gave us a direct proof and direct calculation of the Fourier expansion that matched exactly what the original computation was in Green, Miller, and Vanhove's 2015 paper. Okay, so I'll just end by saying, so in this paper, I think Ksenia had alluded to this yesterday. We have this form for I guess for particular order of vanishing. Our solution looks like this. And there are these alpha terms that arise, and later on, Chester, Green, Pufu, Wang, and Wen had noticed that it seems like for n not equal to 0, these alpha n should be 0. And Danylo, Steve, and I were able to prove that in this specific case of 3/2 lambda equals 12. And I say prove, I mean this very loosely. This is a formal proof. It does involve a manipulation of a divergent series, but we take what they found as the original explicit solution and show that as long as n isn't equal to 0, each of those sums is 0. And we believe that this could be extended to other half integer cases, basically on the form that these, based on the form of these alphas should take. Okay. So of course, moving on, and we hope to make this argument rigorous, seeing if there's a way to avoid using manipulating a divergent series. And we'd like to actually extend the proof to other half integer cases. And then as far as the spectral solution goes, I'm working with Holly Friedlander, Mariam Kwan, Manish Padley, and Ranshu Yu to do the SL3 spectral solution and compute all those coefficients explicitly. So I think it is time for beer, but thank you for being patient for the end of a long day.
Well, thank you very much, Michael.
Just a question about that last statement about the alpha ends vanishing. Yeah, you could check it numerically for the case. Have you done that?
I don't think we have. Oh, maybe
Vanishing for the case.
Oh, Ksenia might be answering.
The answer is that we didn't as of yet. But thank you for a great idea.
Yeah, no, I think she was saying we haven't tried to do it numerically to see what happens, but.
Are there other questions?
Gone.
Yeah, Yeah, in which case can you actually prove that you have an automorphic form? I did not get.
Okay, so that the solution is automorphic.
Yes, exactly.
Good. So that's a good question. So I want to say, so I think that in this classical, in the original case of where the three halves, I guess, oh man, where is it? I guess if we use this method, where is it? Gosh, this method. So where we have something squared, the unwinding the product, our solution is written like basically this. You can translate this back into like a Poincare series, and so in these cases it will be automorphic. But we haven't proven it in the other cases that I've explored. I think that likely there might be other. I know that Daniele and Axel and Oliver probably have done it in some of the other integer cases for using that other method because they also have a Poincare series type solution. So they kind of again work using a similar idea where your solution is given in terms of a Poincare series and is automorphic as well. But I think I'm not sure about the other half integer cases. We have like evidence that it. I think Ksenia mentioned this last time. Evidence that in many cases it should be, or at least it's not in conflict with the right order of vanishing in order to be automorphic. There's that lemma of Steve's and Green and Vanhove that Ksenia put up yesterday, and it's not in conflict, but we haven't actually written a proof for it yet. No, and that wouldn't give us a proof because it goes the wrong direction, I suppose. Yeah.
Well, it's more a comment than a question. You talked about what people call the Hilbert-Polder conjecture. It's neither one conjectured anything,
right?
They published, but they both expressed the thought that an approach to Riemann hypothesis could have two parts. One, as you said, is find an operator the spectrum contains the series of the Riemann zeta function. And secondly, it should be a self-adjoint of course do it. And maybe you don't know because it's something I did well before you were born. Michael Green knows someone's told him, maybe nobody else, but he was a little well known at the time. I solved the first part. I gave a perfectly good function, and I have an operator on a perfectly good space,
right?
Whose spectrum does contain the series, just nobody can make it. I think it's doable. I still think it might be doable to write down at least a candidate scalar product for which it becomes self-adjoint. So there is something. It is, of course, just the Laplace effect.
Yeah.
Not on L2 on different space functions. And that's still be worth now, 40 years later, going back and seeing if anybody, certainly at the time, people like Barry Mays or Danylo, who were at the conference, were very interested. But since nobody ever succeeded in finding a scalar product, of course, then the interest ebbed, but maybe now.
Right, and I believe
later want to try again.
Right, and I believe Elaine Kahns might have a similar type of construct. Did Elaine Kahns have a similar?
I don't want to knock a former colleague. He constructs, of course, you can always make an operator
with
a given spectrum. Just make one copy of the discrete series for every zero. What he does is he takes the zeros of Riemann zeta functions that are on the critical value, essentially makes a copy of the discrete series for each and adds them up. Then that's a space. And of course, there's an operator, but that would be true for any other function. I don't see it. It brings you any. My operator is actually Riemann zeta. It's simply the ordinary one possible. But instead of L2, upper half plane of the SL2 scheme, it's a different space. They aren't plus forms, but are called parabolic forms. It's a different, hyperbolic. It's a different collection of the functions. So there's a different growth product. And so they aren't in L2. The usual scalar product is divergent. That doesn't mean there's not another scalar product tailored to this. But the point is that the eigenvalues
match.
Are efficient. So it might be worth it. We can talk about it.
I would love to talk about it later. No, but I'm very curious if it actually was before I was born now. So you'll have to tell me.
We won't go into details.
I have what's probably a very naive question, but at the end, you mentioned SL3. And, I mean, when you had an early slide that showed there a whole list of other groups that are of interest in string theory. And I was just wondering whether extending this kind of analysis to those groups is it like technically just much more complicated, or are there expected to be new conceptual problems that arise?
Right. So so if you're talking about I guess so using the spectral theorem in SL3, there are going to be no more complications that arise. So back to, I guess, using kind of the original spectral method. But things get more complicated starting in SL4. So the reason is that so the spectral expansion in SL2, in SL3 has a similar flavor to the one here, where the residues of Eisenstein series, I mean, you still just have Cuss forms and Eisenstein series as your eigenfunctions for, I won't say what is proved by Langholms or not, Saul could probably correct me, but I would imagine for maybe any reductive group, maybe beyond that, I'm not sure. But what happens here is for SL4, the residues of Eisenstein series are not as well understood. They're objects called Spey forms, and so that would be not really possible to compute. So yeah, there's obstacles going forward, but we know that the eigenfunctions for these operators, at least. Yeah.
Thanks.
Mm-hmm.
Any other questions? Okay, well, thank you once more.
Yes, thank you.
What? No more talks?